Hello, and welcome to this session today on how to get started with the Nios V and RISC-V IDE for Intel FPGAs. If you could let me know if you can hear me okay, if there's any sound problems or anything, just pop it in the chat, and we'll take it from there. I've got all of the slides and everything that we're going to present today are going to be available at this GitHub repo, which you can see now. So the slide material and the lab material and the step-by-step materials all there, and we'll be running through that. So it's going to take about an hour today to do this. And what I want to do is I'm going to talk to you a little bit about, give you a little bit of background, a little bit of Death by PowerPoint for a little while, and then we're going to move across to using Quartus, using Platform Designer, the RISC-V IDE, and show you how to get together and how to pull together an actual application and build it and run it. You can follow along if you want. I don't know if you've registered or not, but if you've registered, then the registration page, we have some links there, and you can go there and you can get the access to the licenses for Quartus Prime and for the RISC-V generation. Any questions as we go through, please pop them in the chat, and I will try and answer any questions as we go through. I'll take periodic breaks and run through. As I say, it's going to take us about an hour to run through this today, and then hopefully at the end of this all, what we should see, if I just tilt my camera down now, you should see that we have a Agilex board there, and we'll be able to run this simple application on it. And indeed, it is running in the best Blue Peter tradition for those joining from England. It is running at the moment using the application that we've just developed. So let's make a start. Let me make this screen large, and we'll start going through it. So what we're going to do today is we're going to look through a few simple elements. The first thing we're going to look through is we're going to take a little bit of introduction to what RISC-V is, what Nios V is. We're going to take a look through then at how to design the hardware design. So this is the electronics design, the bit stream in essence that goes into the Agilex device. Once we've done that, we're going to look at how we can create our software application. And to do that, we're going to create the BSP, the software application, and then we're going to show how we can download that and execute that on the target processor. Once that's all up and running, we'll take a little bit of a look, and we'll talk a little bit about what we can do with debugging and future steps, and of course future roadmaps that Intel have for their Nios V range. So I want to talk about this. Why do we put soft cores in FPGAs, in high performance FPGAs? And really, you know, FPGAs are fantastic. I'm sure everybody on this webinar knows. You know, FPGAs are fantastic for that parallel processing, that parallel speed, and there's nothing really that can beat them. Yeah, they're a little bit difficult to program and use at times, but they give us that truly parallel performance, and that also deterministic response, and a very responsive solution. And over the years, you know, it's useful though, however, not only to be able to just do that pipeline approach, that highly deterministic pipeline, but at times we also want some sequential processing, some sequential elements in there, and we might use that for such things as maybe simple serial communication across between a host PC and a module, or maybe we want to use the serial to actually configure and program the FPGA and the key elements of it, or the key IPs within there. Or maybe we want to do something a little bit more complicated. Maybe we're running a network stack and we want to run that network stack and we want to use that. So there's a case where sequential processing is really useful in our FPGA designs. And that's where soft processors come in. So one of the most popular soft processors that have been used within the Intel range is the Nios 2, and I've just published a little poll to see who's used the Nios 2 before. But it's one of the most popular processors, the software processors that's in the Intel ecosystem, and that allows us really to offload some of that, to save us having to write really huge and complicated state machines, and to just run it in software. It allows us to architect our system correctly, such that we have some key elements in the processor some key elements running in the programmable logic, and together we get a nice system. And Nios V is the Nios V really is the benefits of this system. You know, Nios V is the next generation, next iteration of the Nios 2. So there's for obvious reasons I'm going to explain in a minute. There wasn't a Nios 3 and a Nios 4. At least I'm not aware of them, but there is now a Nios 5, and it's the next generation. It's the next generation processor from that Nios 2, and it's really what makes it really interesting is because Nios 5, hence the name, is actually based around the RISC-V instruction set architecture, and obviously RISC-V is a very popular topic at this point in time, and a very hot topic. So that RISC-V is quite a good. A nice evolution step. It's quite interesting to see Intel, of course, working with the Nios 5 architecture, with the Nios 5, with the RISC-V ISA. So let's just dispel a couple of things beforehand as we talk a little bit about what RISC-V is. So RISC-V, you will have heard it a lot, but it's actually not. It's not a processor per se. What it is actually, it's an instruction set architecture that processors are declared as compliant against by running against a set of tests. So it gives us a very nice ISA that we can then, as designers, we can then go away and implement them if we wanted to from pure RTL. So we could write a highly parallelized processor, a pipeline processor, or even a serial processor if we wanted to go small, not high performance. And that's the beauty of RISC-V, is that you can go away and you can do that. And obviously with Nios 5, Intel have done that, have saved us from having to do that. They've created this processor that is using and compliant with the RISC-V ISA. But there are actually 3 instruction set architectures that have been ratified by the RISC-V open source community. And they are the RV32i, the RV64i, and the RV128i. These are respectively a 32, 64, and 128-bit buses, respectively, for these. So we're going to be working with a microcontroller class RISC-V, which is what the Nios 5 is, and that's going to be in the RV32 area as well. Now there's a range of other elements as well. And someone's just asked a really great question, so we'll talk about that in a second. But there's a range of other extensions that can be added on to the RISC-V. So you can have it for atomic instructions. We can add support for integer multiplication and division, or double and precision floating point extensions. So what we're going to be looking at today is we're going to be taking a look at how to create the Nios V, the Nios 5M, which is basically a microcontroller class Nios 5 application. There are more advanced codes coming. If you take a look on the Intel website, you know there's a planned range of these, including for the application class and a Linux capable class one. But the Nios 5 that we're talking about today, the microcontroller one, is based around the 32-bit instruction set, and it has support for atomic operations. Now, someone has just asked a question, which is really great, about if it's the open source nature of the RISC-V ISA and the ecosystem, will it be compatible with Nios 5? And that's one of the really nice things about this, is that because it's compliant with that ISA, then anything that you can, if you compile software for targeting the same RISC-V architecture, the same RV32 architecture, it should run on the Nios 5. Now, obviously, that doesn't incorporate the rest of the system. You know, you'd have to handle where the addresses are for the peripherals you've put on there, and if you've put any special custom instructions in there that aren't in your Nios 5, you would have to address that. But in principle, it gives you a nice flexible solution for leveraging and building on this open source community. And I believe if you read some of the Nios 5 documentation that Intel have put out, you know, they seem very committed to working with the community and developing that RISC-V architecture there. So we can see it's a really simple processor. This one we're going to look at, the Nios 5, the Nios 5M. It has the standard sort of, the program controller and the program controller and address generation. It has the exception controller, the registers, the ALU. So it's a very, very low level, very stripped down, very small processor intended for sort of small applications, bare metal applications, small OS applications that are using Micrium OS 2. Additionally, we can add the debug agent to it, so as we can debug it, and we can add the interrupt controller as well, and the breakpoints as well if we want to for our breakpointing. Now, what's really interesting about this is obviously it's a Harvard architecture. So we have a instruction bus and a data bus. Both of these in this instance, they're 32-bit. In other instances, the RV64, they would be 64 or 1 to 8 in the RV128. And this is what we're going to connect into our peripherals. So into our memory system when we're working with Platform Designer, we're going to be connecting in this instruction bus and these data buses into our peripherals. And all we're going to be doing, giving it else as well, really simple. We're not really going to worry too much about this debugger interface down here, but we're going to be giving it clock and resets to get it up and running and get going through it. It's really simple, really simple, really nice, and it's a good processor as we step through this. So, like I said, let's talk a little bit about some of the architectural features of this. We have AXI4 buses for the instruction and data memories. We get, obviously, when we work about the performance of these processors, we often use the parameter Drystone millions of instructions per second per megahertz to be able to give us some idea of the computational power that the processor can provide us as a developer. And in this instance, it provides about 0.464 DMIPS per megahertz. So the faster we run it, the more performance we would get. Now that's quite an interesting one because the most direct comparison for this is the Nios 2, the smallest version of the Nios 2, and that gave just over 0.1 DMIPS per megahertz. So again, we're seeing like a 4 times increase in the performance of this Nios 5 compared to the previous Nios 2. Now, currently, as they're rolling out the Nios 5, it's only supported in devices like the Stratix 10, the Agilix, and so on. So it's going to be rolled out across a range of devices as we go on. And one of the interesting things in sort of the size of this is it's going to vary between sort of 1300 and 1600 ALMs in our application when we implement this, and it can give us some really good performance. In a Cyclone 10 device, we can see it operating at about 270 megahertz, and in the Agilix that we have today, my example's not running at that. My example's running a lot slower than that because it's just a simple hello world example. But in the Agilix, it's going to be running at about 566 megahertz in maximum. So we can get some really nice high performance processing out of it, and it fits really nicely within our FPGA world. So to create this is going to be really quite an exciting project to step through and work. We're going to use a range of tools today. We're going to use Quartus. We're going to use Quartus Prime to do the actual project and run through that. We're going to use Platform Designer to capture the platform, to define the platform, and to generate the addresses, the RTL, and everything. We're going to use the Nios 5 shell to create the application, and we'll talk a little bit more about that as we go on. We're going to use the Aisling RISC-V IDE to create the software environment that we want to use to debug and to process our system and work out, to download and work out what's going off in our Nios system. We're also going to use CMake, so the flow for software is going to be very CMake based, and we'll obviously make use of make files and such like doing that to build everything through and to build our system. So it's a fairly straightforward, fairly linear flow. I see from looking at the looking at the poll, roughly about 50 of you have used a Nios V before, compared to that. So there's a few little, compared to the Nios 2, there's a few little tricks and tweaks, and there's a few little modifications as well that have been made to the tool flow to make it slightly different in how that works. Perhaps to what you might be aware with if you were using a Nios 2, for example. So just to give you some introduction to the tool chains, I'm just going to give you a little bit of one slide on everything as we run for each of the tools. As we run through, you can see the graphic on the right there shows what Quartus Prime looks like in its main application, and you can see it running the project that we've created for today. But what we're going to use Quartus Prime for is we're going to use this to create the implementation of the programming file. So we're going to use this really as our project management, as our flow control, as our project control. We're going to use it to do the pin allocation, to set the I/O standards for the pins that we're using. We're going to use it for setting up the security and the SDM element that exists on the Agilex device. But more importantly, because if we want these devices to run at high frequencies, such as 560 megahertz or something, then we need to make sure we've got accurate timing constraints, and we've done timing verification and timing closure. And Quartus Prime is going to give us all this ability to do this. And of course, as well, it's going to allow us to work with IP, generate simulation models. It's going to give us that nice ecosystem that allows us to create and implement our programming files that eventually we will program into the Agilex board. Now, at the heart of this, where we're really going to be working today, and where we're going to spend a lot of our time, is in Platform Designer, and this is where we're going to create our processor subsystem. And in this, we're going to add in the IP that we want to use. So we're going to add in the Nios. We're going to add in the Nios V IP. We're going to add in the JTAG UARTs, the on-chip memories, any additional peripherals that we want to use. We're going to add in and drop them in there. Then we're going to connect them in the way that we want them to be connected and interconnected. And we're going to do some analysis and some generation of that. And if we've got custom IP that we're using, so custom RTL that we're using, we can pull this in as well from our previous designs or from our RP library. Now, one of the big key differences between this and previous generations with the Nios 2, for example, is Platform Designer was used previously with Nios 2 just to create the processor. The board support package was actually created using the software design tools, using the Eclipse software design tools. In this instance, though, in these applications going forwards, our solutions, we're going to create the BSP using Platform Designer, because that's where we create it now. And what we're going to do within Platform Designer is we can also make available I/O to the high level of design, such as if we want to take this IP block that's available that we create within Platform Designer, we can take that and we can wrap it in HDL or a wider application for our system if we want to. And what this gives us, it gives us a really nice, really flexible, really configurable system for our Nios processor. We're also going to use the Nios V shell, and this is a command line project. That's the command line set of tools that are included with the Quartus Prime application when we load the tools. And this gives us the ability to create the BSP or to update the BSP as well, to create applications. So we have to use the Nios V shell to create the application, and I'll show you exactly how to do that if you take a step through as we run through this lab, or when you get to the when you run to the labs. And what we can also do is we can use that to download the target, and it'll also give us some nice information on the stack and the heap. And in fact, on the right there, you can see what's going to be one of the outputs from this project is showing the Nios V running and pushing it out over the UART terminal. So we can use the UART terminal in there as well, which makes it really quite nice and integrated. Now, obviously, it'd be nice to think that we wrote our software correctly and we never need to do any debugging. But you know, the world exists. We do need to do this, so we can use the Aisling RISC-V IDE here, and this is an Eclipse-based IDE, and we can use this to create to bring in the applications to generate our application further, to create further applications, further advances to our applications, but to do debugging. And if we're working on boards with a hard processor system like the Agilex, then we can also do debugging of the A53 cores as well as what might be in the logic running as a soft core. So to get started with this, you know, the applications and libraries that we create using the Nios V shell have to be pulled in, and they have to be created using the shell, and they have to be imported into the RISC-V IDE. And as we go through the software side of the lab, we'll show you how to do that. But it is relatively straightforward and simple. And we'll see then a nice and simple example, an application just like we can see here, where we can run it and say hello world and get to a position then that we can go away and continue further with building upon our Nios V system. So our flow today is going to look very much like this, in that we're going to have a library of Nios V IP cores and standard components, and that's going to be provided by Platform Designer. We're going to say, hey, I want to start creating a project, and we're going to go through creating the Nios V project in Quartus Prime. We're then going to go through the Platform Designer, building the Nios V based system. We're going to generate that platform. We're going to integrate that within Quartus Prime. Now, in the interest of time today, I'm not actually going to synthesize and compile it. It doesn't take that long. It takes about 10 minutes, but I figure the last thing anybody wants to do is sit and watch me build my machine building for 10 minutes. Once we've done that, we're going to run through. We can do the pin locations, the timing, any timing constraints. We're going to do compile the hardware and get that soft file out such that we can program it into the Agilex board. Our software flow is going to look very like this. We're going to start with the BSP that we're going to generate in Platform Designer as we go through this. Once we've done this, we're going to create the application, which is a CMake based application. So it's going to be a CMake based flow, and we're going to do that using the Nios V command shell. And once we've got that, we've got two options. Then we can import the BSP and the CMake build file into Aisling's RISC-V IDE and create a visual debug environment such that we can connect to, download and debug into it. Or we can use the Nios V shell as a command line to build the application and then download it in there. I'm going to show you the Aisling RISC-V approach today because it's a little bit more interactive, a little bit more hands-on, but you can do it in both directions. So I'm going to get this at this point now. We're about to start with the lab. So I'm going to minimize PowerPoint. And then we're going to come over to what would be, yes, I do want to exit that. We're going to come over to what would be Quartus Prime. And this is the environment. This is what we're going to be working in. This is my test from earlier on, so you can see I've programmed the board. I've run the tests, and it's all come through. And it's all looking good, but we don't want any of this yet. This is all just to prove that we can do it. Yeah, we'll save the changes to that. We have the Nios V IDE open. We'll close that as well for the time being, and we'll just leave ourselves in Quartus Prime. Now, what we're going to do is we're going to close this project. And as we get any questions, or is anything in the chat, then feel free to go through, and we will do it. Zooming with a lower resolution, it's hard to see. Let me work out how I can do that. Give me 1 second, and we'll see if I can change my display settings here and just drop the resolution a bit. So maybe if we drop it to that. This is 2. Hang on, let's identify these. Yeah, this is 2. So let's just drop that one. For the time being, and then there. So hopefully, I don't know if that makes it better, if that makes it easy to see. Let me know if you can see that better in the screen. That's perfect. I should have apologies for that. I should have thought about that before I started. I use a 4K monitor. I never figured it would be so difficult to see on the screen. So what we're going to do is we're going to come in here. We're going to create a new project using the new project wizard. And in here, we're going to select the location of our project. In this case, I'm going to change it slightly. I'm going to do it in HDL projects. I'm going to create a new folder. I'm going to call it Intel Live. And then under Intel Live, we're going to call it Nios V. And this is going to pull through, and it's going to show us the name of the exact name of the top level entity that we're going to use, and that should be better there. So I was just asking if this is recorded. So yeah, it is recorded, and it will be available on demand within about 5 minutes of this webinar being completed. So once we've got that, we're going to click on next. We're going to create an empty project, although there is a range of projects on the design store if you want them. To get you started, we're going to click on next for this one. And then we don't have any files to add as well, so we're going to leave these blank for the time being. And then we're going to enter our device that we're looking for. I'm working with a Agilex F series. So we've got the Agilex F series, and we are looking for, I'm using the production version of the Agilex F series SOC transceiver test board. So we are looking for the AGF014R24E2V, which should be this device here. And it's a good job I got it written down next to me, so as I didn't have to try and remember that long part number off the top of my head. So we'll click on next. We're going to leave the design tools and everything. We're going to leave those just as they are, and we're just going to create a nice, simple, standard project. This is going to give us a summary then of what we're targeting and what we're running through. And actually, at the end of this, I'm going to switch back from the software view. We will run it from the software view through the project that already exists, just in case I make any errors and anything as we're going through and it's live. So we're going to click on finish. And you'll see this opens our project environment now. You can see we have a top level file. We have the project navigator under here. We have the flow navigator under here, so as we can go through the completion of it. What we're going to do is we're going to open Platform Designer. And in Platform Designer, we're going to save everything. We're going to see, this is what we want. We've got the Quartus project. We've got the revision we're going to call it Nios V. We're targeting the Agilex device, and then where our Platform Designer is going to be can't be stored in there. So we're going to create a new one of these, and I'm going to call this Nios V. I'm going to create that, and then we're going to create that. So we should see this after a few seconds saying that we've created a new subsystem. And once we see this go green, we can close it. And I'll just pop this out and expand it now so as we can see what we have here. What we get here is the beginnings of the system. So it gives us just a very simple clock and reset bridge. And these just give us and passes into and out of the clock and reset into and out of our system. So our clock, we need to set for the correct clock rate that we've got on our system. In this case, we have a 100 megahertz clock. So I'm just going to change this to be 100 for my system. And on the reset, we have to make sure, really critically, because I learned this the hard way while I've been running through this several times. In preparation for this, we have to make sure, of course, that we've got the right reset polarity defined. So we need to check and control whether we've got the reset correctly showing, and that should hopefully show where. So that shows when we click on that, and we can click on active low, and that should give us the nice active low signal as we go into it. Now what we get over here, let me just change this setting to show all IPs. We get over here, we get our system, and this is where we're going to begin to create our system and put everything together. So we're going to come over here, and under processors and peripherals, under embedded processors, we should see our options here for Nios V. So we're going to double click on that and add that in there. And that should, once we've done that, that'll give us this option here at the moment. At the moment, we can see that we can't see the reset agent or the exception agent, but we can see that, and we'll use that momentarily to help us set up and configure it. We don't have any other changes that we want to make at the moment. We can see we've got the instruction, the data, the resets, and everything. If we want to get some example designs, we can pull these in from the top, which is always good. But for the time being, we're just going to click on finish. And what this should do is this should download and add us in. It should add us in the Nios V processor into the system. And I'm just for those that are following along on the instructions, I don't know if anybody is or not, but if you are following along on the instructions, we are just on. We are just on stage. We are just on. I can't remember. I didn't put the page yet. We're just on page 29. So we get that. So we have our Nios V system installed, the basics of it. Obviously, we don't have any connections or anything here. And what we want to do now is we want to add in the remaining elements of the design such that we can run through it. So we're going to add in the JTAG UART. Can't type today, JTAG. So we're going to add in the JTAG UART. And again, I'm not going to make any changes to it. I'm just going to click on finish. And we're going to add in the on-chip. On-chip. Must be all one word. On-chip memory 2. And we're going to add that in to the design. Again, I'm not going to, the only changes I'm going to make to the on-chip memory is I am going to make it much larger, such that we can fit in a memory size in there. So I'm going to make this 65536, or if you want to, we can make it even larger than that if we want to. Let's actually make it a little bit larger. We'll make it 131072, and that should give us plenty of memory to be able to put our application in. Our application is going to be running from this memory, so we need to make sure that we've got a suitable size of memory. You have to be careful that some software commands, some elements can actually be quite large and have quite a large footprint. Once we've got that, we're going to click on finish. And this is going to give us the basics then of our design. And we can see that we have the Nios V, we have the clock and the reset, we have the JTAG UART, and we have the Intel on-chip memory. Now, none of this is actually connected, as you can see over here. None of this is connected at this point in time. So we're going to go through and we're going to do some basics. So we're going to connect the clock bridge. We're going to connect the clocks to the JTAG UART, and we do that by clicking this little dot here to connect them through. And we're going to do the same with the reset. With the reset out, we're going to connect the resets to all of the resets, and that makes it nice and simple for us to do. Now, obviously, our instruction and data manager that are within the within the processor, they need connecting to the on-chip memory. So we're going to connect both those to there. So the processor can access the memory to get both instructions and to get data, and that's important. When we want to send data over the Avalon, the JTAG to UART to transmit and to tell us what's going off, we click on this. We're just going to connect the data manager to it. There's no need for us to connect anything. We don't need to connect that instruction bus. So we can see our system now. We've got a fairly straightforward and fairly simple system. There is one thing we need, and I need this just because of the Agilex device, and it's called the reset release. So we're going to add in the reset release IP just in there for the reset system. And we're going to make it a reset interface, and we're just going to use this to gate the resets. So this just makes sure that the device is done and configured and programmed before anything tries to run through and drive our resets. But this is predominantly our system, and it's all set up and running nice and simple. Few click buttons, few along the way. What we need to do now, though, is we need to go back to our processor. And we need to make a little bit of a change here, in that we can change tell it such as when it's reset, that it goes from the reset into the memory. It goes looking in the, I've told it the wrong one, into the on-chip memory. And again, if we get an exception, we go to the on-chip memory as well, and to a specific offset in that on-chip memory to pick up and to run through. Now, the other thing we need to do, obviously, we've got a system, but if we look at it at the moment, we don't have anything. All of the addresses are conflicting. Nothing's working nicely. So we're not going to be able to have a fully working processor system because all of the addresses are going to conflict. So if we go to system, then we can do assign base addresses, and that will run through for us, and it will assign the base addresses. We can go back to the system view then. And we might also actually want to connect this interrupt into the processor. And this is still red, so there must be something I've not done. Reset agent on is out of range of absolute. So I'm just going to generate that address map again. There we go. That looks better. So there we go. So we're all nice and good to go now. And then if we want to, just because we're paranoid, we can sync we want to make sure everything's good, so we can synchronize the system information, which will take a few seconds. We can validate the system integrity just to make sure that we've got a nice system integrity there. And then we can come down here, and we're in a position now that we can generate our RTL that we're going to drop out and pull through and compile and use in our Intel system. If we want to, we can choose which flavor of language we want. I tend to, even though I'm a VHDL guy, I tend to leave it just as the default sort of Verilog. And we can run through, and we can click on generate. Now, this will generate through. It will run through. It's asking if you want to save changes first, and it will run through, and it will generate the RTL that we're going to put in our system. So hopefully this takes long. Sometimes it can, sometimes it can't. But if you've got any questions, then please just or the question. I noticed my camera's going a bit duff as the processor's actually building, but hopefully it'll be okay, and it'll come through. And we'll get there in a second or two. If it doesn't, I'll stop it. If it doesn't look like it's making much process, I'll stop it, and we'll switch over to the other one. But we can see it's running. We can see it's running through there, and it's going through. So hopefully this will finish generating all the HDL files that we need for creating our solution. And it'll get through that. But yeah, any questions as we go through, then please just ask them in the chat or the questions window. Go take a look at the poll. There's a poll running. I want to know who's used Nios 2 before. So far, slightly more people have than haven't, but it's roughly sort of 51%, 49% as to who's used Nios 2 before or not. Once this is run through, we'll get this completed, and that's done. So we can close that then, and we have our RTL files such that we could implement them if we wanted to in the FPGA. Of course, what we need to do as well is we need to create a board support package in this as well. So what we're going to do is we're going to click on New BSP here. We're going to give it a location to store the new BSP. Now, I'm going to give it one of these is going to create me a new folder. So I'm going to create a new folder. I'm going to call this BSP, and I'm going to put my BSP under the BSP. Let's call it Nios V. Create. So this should give us a nice example of what we're going to do for the BSP. We have to tell it where the Nios V system is that we've just created. So this is the Quartus system that we've just created. Once we've done that, we should see, as it pulls in, we should see it picks up and it tells us which of our processors we're using. So in this case, we've only got one Nios V, and it tells us which of the operating systems we want to use, whether we want to use Micrium or whether we want to use the Altera HAL. So I'm going to use the Altera HAL. And I'm also going to use a slightly different, it's going to drop into the BSP directory anyway, so I'm going to do that. And then we're going to click on Create. And this is going to create us a board support package for our application. Only takes a few seconds to do. What we'll see is while we've got this system view in the middle now, we get this BSP editor and drivers over here. So let me just move this across a little bit so as we can maximize and we can see what we've got. But we can change all the configurations of the hardware acceleration layer. We can see that we've got the standard in, standard out, and standard error all going to the UART. We don't have any system clock timers in here, so I'm going to set these to none for this example. And if we want to, we can use the reduced size drivers, such as opposed to doing interrupt driven stuff, it will do polled. It will do a polled approach. But take a look through, you can see all of the software packages. You can see how the configuration of the linker scripts. You can see the BSP generation and the target directory. For our application, we don't really need to make any changes to this. There's some interesting things under the advanced. For example, if you want to enable login and log out over, in fact, we could do that and log out over the UART ports as if you're stuck and you're doing some debugging. It will do that. It will do that for you. What we can do then is we can generate the BSP down here, again asking us to save any changes that we've made, and this will generate the BSP that we can put into and use within our software application. So now we can close that. We can close Platform Designer. That will not generate now. We'll just skip and we'll do that now. And we should see that we've now got a system that we can begin to bring through and implementing our solution. What we'll need to do is we will need to, if we just run the analysis and synthesis, hopefully this shouldn't take too long to run through. We can then run through and we can do that. Someone is just asking a question: is it possible to see the output of the hello world on the model sim transcript in case you do not have a board? You should be able to simulate it and see the applications running. You might have to do something yourself that's a little smart if you wanted to actually see the waveform that's coming out of the JTAG UART, for example, to see that going in the to see that and work out what that is. So this is going to run through and it's going to take us through. What we need to do then is we can take a look and we can generate our pin assignments and add in the pins and the IO assignments that we've got within our application. We've only got 2 pins. Obviously, we've got a clock and a reset. If you're targeting this board, we're targeting pins for the clock is U52 and it's G52 for that negative reset, and they're both on a 1.2 volt rail. In the interest of time, though, while that runs through, we can actually see that now. This analysis and synthesis is done, so maybe we can. It's on this one actually, isn't it? On the pin planner, we should be able to see the application and run through. But in the interest of time, I'm going to minimize this now, and I'm going to go to the so we can see our resets, and we would assign them to the locations and the banks there. Now, because I'm going to use the pre-existing design for this, because we don't have time to build that, I'm just going to take a little bit of time, and I'm just going to go to my installation directory, where my installation directory is. I'm going to find the Nios V. I'm going to find the thing called bin, and I'm going to run the Nios V shell. Once we've got this, what we're going to do is we're going to create our first application. So I'm going to change directory to where my software application is. So this happens to be on my C drive, so I'm going to change to my C drive. And then I'm going to remember that I can't remember where I've actually stored this on my C drive. So it is under Nios V software application, and it's under. I'm going to just copy this file actually. We'll put it under Intel Live. We'll make a new folder called software. And we'll put that one under there for the time being. Right, so now we've got this, what we're going to do is we're going to change directory into this CD. And this main.cpp, it is purely just a simple hello world program that I will show you in a minute. Now, if you want to see the help, we can just type in use a --help to see that. Actually, what we want to do is we want to create a new application. So we're going to use the command nios v-app. We're going to tell it where the BSP is. So the BSP resides at a directory above called BSP. We're going to tell it where the application directory is, which is this directory. And then we're going to tell it where what the source file is, which is main.cpp. Unrecognized switch. Oh, it's A equals. And what we'll see there, so this has created because this is a CMake flow, this has created the application. So we can see now that on the file here, we've got a main.cpp and a CMakes list.text. And if we open up the CMake list.text, we'll see that this includes all of the things to compile the BSP and to compile the main application. Now, what we want to do now is we want to open the Aisling RISC-V IDE. So we're going to do, in here, we're going to do RISC-V. This is going to open the Aisling RISC-V IDE. And I can see somebody's asking some questions about Nios 2 and the EDS and where it's built into the Quartus and how it's all going to come. I believe that Aisling RISC-V does come with the Intel Quartus installation when you're doing it. So when you download it, the RISC-V actually comes with it. So I didn't install this separately. It just came when I downloaded and installed the project as well, the Quartus tool. It's going to ask us for a workspace, and this is a workspace. So I'm going to give it a new workspace because this is the one I've been working with previously. So we'll go to my HDL projects. We'll go to Intel Live. And we'll just create a new folder here, and we'll call it workspace. And under workspace, we will then launch that. No, you can use. Someone's asking if you can use C or C++. Both are supported. So what we're going to do, come in here, is we're going to come in here then, and we're going to take the option of creating a new project. We're going to click from the C ones. I'm going to click C project because that's what we're doing. I'm going to click on next, and it's going to give me two options here. So the first thing I'm going to do is I'm going to select it CMake driven. I'm going to give it a project name. I'll call it Intel Live Software. And I'm going to browse this directory to the directory where my software application is. So I'm going to go to this software. That's the software directory now. And I'm going to click on next and then on finish. And then hopefully what we see here is we see our main.cpp and we see our CMake list, and we can build this. And hopefully this will build and compile. So it should build, and under the build now, under the debug, obviously we've got a RISC-V ELF file there that we can download and run on our machine. Interestingly, if you want to take a look at it, you can take a look in the build console, in the various views of the build console, and one of these should show you the compilation and the size of all the software and everything that we've got to. We've got the object dump there. We've got our main.cpp. Our main.cpp is dead simple. It's just going to loop around 1,000 times and print out hello world and do that. What we want to do then is we need to create a simple application. Now we need to download the process, the soft file into the Agilex device. Now, in the interest of time, I've already done that, so it's already running on this Agilex. But we can do that using the soft file from the Quartus programmer. And what I'm going to do is I'm just going to create a simple debug configuration here then in this instance. And we're going to go with, I'm going to make this a little bit bigger so as we can see it all. We're going to go with RISC-V, Aisling RISC-V Auto Detect. We're going to hit the new button here. It's going to think a little bit. It's going to come up. It's going to ask us what the project is. It's going to ask us where what the project is. Oh, sorry, that's the wrong one. Search project. We're going to give it the software.elf that we've already created for our software name. We're going to go to the debugger, and we're going to see that it's connected over the USB 2 blaster that's already connected onto the Agilex device. We're going to do the auto detect scan chain. So you can see here now it's detected the FPGA type, and it's detected the Nios V core that's in there. So hopefully now, fingers crossed, I'm going to drop this code just a little bit, just to be on the safe side today, and then I'm going to hit debug. And there we go. We can see it connecting to the RV32. Yeah, we'll switch to the debug perspective. And we can see then that the exact same application is downloaded, it's installed, it's running, it's paused its execution. What we can do then, if we want to see the JTAG UART, so we can do JUART-terminal in this window, and then let me just minimize, put the two side by side a little bit. And we've got the two side by side. And if I hit run, what we should see is we see the UART terminal. We see the software running on the application, the UART terminal updating, and then showing that output there. So this is a bit of a whistle-stop tour into the Nios V. I do admit that, but we've taken, in the last hour, we've taken a little bit of a look at what's included in creating a Nios V system, the various tool elements that are included. We've looked at how we can create the project in Quartus Prime, how we can architect the processor within Platform Designer, how we can create the BSP within Platform Designer, and then once we've done all that, how we can come out and we can, using the Nios V shell, we can create the application import it into the Aisling RISC-V IDE, and then download and run and execute a simple application on the processor core. So it's a really straightforward, really relatively simple application. I do accept that, but I find often sometimes just showing people the flow and the steps allows you to then pick up the ball and start running with it and take a think about whether you would use Nios 5 in your next application. I have a poll, a last poll, which we'll take a look at if you're going to consider using Nios 5 at all in your next system in place of sort of Nios 2. And that would be really interesting to see and to see your thoughts on it. And we've got a few minutes left, so if there's any questions, I think I've tried to answer all the ones that are in the chat window or the questions window. But if you've missed anything, if you want anything recapping, please just give me a shout and let me know. If you go to my GitHub, and I'll put that link, the GitHub link, in the chat again, just to make sure it's not being lost. But if you go to the GitHub, you'll see my email address and such like and everything. So if you start going through this, if you take a look through it and you hit some problems or you hit some questions and you're not really sure what I did, then please feel free to reach out and say, hey Adam, why did this? Why did you do this? Or why? Oh, I'm doing this and I don't see this. And just let me know, and we can take it from there. But apart from that, thank you very much for attending and coming along. I hope it's been of interest to you today. If it has, let me know. If it's not, definitely let me know. And we'll take a look at another Intel FPGA soon, and another sort of Intel application, and working out what we're going to do with that. So I'll begin to wrap up if there's no questions. So thank you very much, everybody, for coming along. And like I say, yeah, any questions, just pop them in the chat. I'll be here for a minute or two. And yeah, thank you for attending. So someone's just asking actually if the Nios 5 used shell will require WSL. I don't believe it does. I know the Nios 2 flow does, but I don't think the Nios 5 flow does. So that's a good. So someone's asking. That's a good question. I'll create some blogs. I don't know if anybody's familiar with my website. I'll pop it in here. But there's at duvoengineering.com. I'll put some Intel blogs up showing you how you can simulate this if you don't have a board that can do it. But with that, I will thank everybody, and I'll end this event now. And thank you very much for coming. And yeah, let me know and reach out if there's any issues.